We're going to talk about a couple ideas today. The first one is an idea called a differential. Mostly it's a vocabulary word. It's stuff we've been looking at already, but it's kind of giving it a word, I suppose. So if I said, find the differential, I'm using hot pink today. Find the differential of the function. All that's saying is, what is the equation that will indicate the way y is changing as x changes? So let's just do one that's somewhat simple. So if I said y equals 3x to the 2/3. So basically all this is saying is find the derivative, but then we're really curious about how only y is changing, not how y is changing. I guess I should say as x is. Let me show you what I'm talking about. So if we find the derivative of this, it's dy over dx, and then multiply the 2/3. So we're just using the power rule, and then subtract 1 from the exponent. So if we simplify this a little bit, this is 2 over the cube root of x. So what the differential though is saying is, how is y changing? How can we calculate the change in y? So if we just isolate the dy, multiply or bring the dx over to the other side, dy equals 2 over the cube root of x dx. That's a differential. So it helps us figure out, if we know how x is changing, how is y then changing as a result? Okay, good. Now, why would we care about that? I tell this story every year, and I swear to you, it's absolutely true. Absolutely true. I'm not making a single word up. I'm trying even to make it word for word. We met these people when we rafted the Grand Canyon, I don't know, 20-ish years ago, and we became friends with them, and we would hang out, and we would go on river trips for years afterward together. And one time we're sitting around a campfire, we're on the beach on the Middle Fork of the Salmon in Idaho. Gorgeous river. If you've never done it, I highly recommend it. So we're sitting around the campfire, and my friend Bob, he says, all right, Kathy, we've got this round, was it square? Yeah, it was square. We've got this square piece of wood. Sorry, I swear I'm not making it up. I'm telling you the truth. I have this square piece of wood, but we want to make a round table out of it. So I want to know the largest diameter that I can make out of this square piece of wood. So he gave me the dimensions, and I, Pythagorean theorem, and I said, so it's like the square root of 84. That part I'm making up because I can't remember the number. I said, so it's like the square root of 84, whatever that is. And he said, wait a minute, you're a mathematician? You don't know what the square root of 84 is? I'm like, no, a little more than 9 and less than 10. I don't know, 9 point something. And he was just baffled. He couldn't understand why I didn't know the square root of 84 without a calculator. So I'm going to show you one of two ways this year on how you can estimate pretty close the square root of 84 if somebody ever asks you while you're sitting on a river around a campfire one day. Hey, and if it happens to you, I expect a phone call or an email telling me that it happened to you, because it will one of these days. So here's how we can do it. So we're looking at the square root of 84. I'm going to get a whole new page here because I think this is worthy of a whole new page. If I look at the graph of a square root function, let's just start there. And I'm going to try to make this, whoops, thank you, Notability. I'm going to try to make this as big as possible so I can, let me plot some points. Square root of 1 is 1, square root of 4 is 2, 5, 6, 7, 8, 9. Okay, this one is to scale. I'm going to use a number other than 84 right now because I didn't want to use a really large graph. let's say somebody asked you the square root of 5, and you might already know it, but let's just say somebody was asking you the square root of 5 on the river somewhere out there in the world. Well, we know the square root of 4. We know that's 2, and we know that square root of 5 is pretty close to it, so we know that the square root of 5 is 2 point something pretty small. It's pretty close. Well, this function here is going to help us because we know a little bit about calculus now, and we know a lot about lines tangent to a curve. So what we're looking for is when x is equal to 5, we're wondering about that point right there. Well, if I can draw a line, I'm going to use a different color now, tangent to my derivative, or tangent to my function, square root of x. I'm going to see if notability can get me a little more tangent. That's almost perfectly tangent. If I zoom in, look at how close that tangent line is to the actual function. That's almost an exact. I mean, it's not exact. It's only touching the function at x equals 4. However, at x equals 5, that tangent line has almost the exact same values as the function itself. Now look what happens as we get further away from 4. That tangent line is no longer a good approximation because that tangent line starts to diverge or go away from the square root of x graph. So if I can write the equation of this tangent line, I can use it to get a pretty close approximation for the square root of 5. Now, would I recommend this if you were working on the space shuttle and people's lives were at stake? Absolutely not. However, because we're just helping Bob make a round table out of a square piece of wood, this is going to be pretty darn close. So what I've done was, square root of 5 is what I was looking for. I found the function that was relevant here, and in this case the function was the square root of x. And then I found a really convenient point that was as close to the value we're looking for as possible. Now if we were looking for the square root of 7, it would be kind of a wash on whether I would use 4 or 9. Probably use 4, but because of the way this graph grows, I'd kind of look at it and try to decide, would it be better to use 4 as the convenient point or 9 for the convenient point? So it's at this point it's a judgment call because we're estimating anyway, so it's not going to be perfect, but it'll be close. Now, what we're going to do is at this convenient point, we're going to write the equation of that tangent line, and we're going to use that tangent line to approximate what the square root of 5 is. So this is what's called local linearization, because what we're saying is if we focus in on this one point, if I could zoom in even further, this looks like a straight line in your graph. So it's almost like we're saying, let's just look at this tiny little chunk of the graph because it's almost linear there. And let's see if we can estimate using that linearization. Okay, so let's do this. Let's answer Bob's question. And I'm going to use the square root of 5 for now, and I will do the square root of 84 because that was closer to what he was asking. All right, so let's write the equation of the line tangent to f of x. So the line tangent to f of x equals the square root of x at the point 4, 2, because 4 was that point that was really close to the one we were looking for, and we know the square root of 4. That one's convenient. Okay, in order to do that, we know we're going to use y minus y1, we're going to use point slope form. We know the x and the y, so we know this is y minus 2 equals m times x minus 4. What we need to find then is this slope, in other words, the derivative at x equals 4. We've done this before, but now we're trying to use it for some purpose. All right, so let's find the derivative. F prime of x equals 1/2 times x to the negative 1/2. And this is why I always am adamant about not having a negative square or a negative exponent because I can rewrite this as 1 over 2 times the square root of x. So here's the derivative. I know the convenient point. The convenient point is at 4. So f prime of 4 is 1 over 2 times the square root of 4. Square root of 4 is 2 times 2. We know the slope is 1/4. All right, we have the equation we need. Y minus 2 equals 1/4, saying one thing, doing another, times x minus 4. Okay, this is the line that's tangent to that curve. That's this green line that comes really, really close to the function. If I plug 5 into that tangent line, I'm going to get a value that's really quite close to what the actual square root of 5 is. So let's see if we can do that. I'm going to plug 5 into that tangent line. See what we get. We got y minus 2 equals 1/4 times 5 minus 4. 5 minus 4 is 1. 1 times 1/4 is 1/4. And then if I add the 2 over to the other side, I get y is equal to 2 and 1/4, or 2.25. Okay, I've got my handy dandy calculator. Let's look at what the actual square root of 5 is. So I've got my calculator on my phone. I'm calculating the square root of 5, and I got 2.2361. Pretty close if you're building a circular table. We're only off by, what, 0.014-ish? That's pretty good. Like I said, if you're building the space shuttle, not close enough, but for what we're doing, pretty good. So it's a tangent line approximation, or we're using local linearization to do that. Okay, I'm going to give you a chance now. I want you to answer the question that Bob had for me. Will you please take a moment, pause this video, and I'd like you to estimate the square root of 84. I'll give you a moment. Okay, we're using the same function. We're still using that square root of x function. So this is the one that we're going to help us determine the line tangent to this graph. And I'm going to find a point that's conveniently close to 84 that I know a little bit about. So I know that 81 is a perfect square that is close to 84. 100 is the next perfect square. I think that's a little too far away. So I'm going to use 81, 9 as my convenient point. We found the derivative up above. That's 1 over 2 times the square root of x. We know the x value, our convenient point, is 81. So I know that this slope is 1/18. Okay, if I write my equation out, y minus 9 equals 1/18 times 84 minus 81. 84 minus 81, that's 3. 3 times 1/18 is 1/6. Plus 9, I get y equals 9 and 1/6, or 9.16 repeating. Okay, in my handy dandy calculator, I'm going to find the square root of 84. The square root of 84 is actually 9.165. Not bad. Whoops. Not bad at all. Pretty good for a river. All I would have needed was a stick and some sand to write this stuff out, and I would have wowed my guests, and my friend would not have ridiculed me. So keep this in mind. This is a good thing to have. Another way we could use this is if I asked you, for example, to estimate the sine of 3. That might come up on a river. I don't know, but I know that the square root of 84 definitely will, because it did. The sine of 3, though, if I'm asking you to estimate the sine of 3, well, I know that the function that we're speaking about is the sine of x. So if I were to graph the sine of x, it looks like this. And I know that 3 is just here, just before pi. So I'm going to assume that my value, so if I were talking to Bob, I'd say, I don't know, it's close to 0. It's going to be positive and close to 0. Not good enough for Bob. So we're going to use the convenient point that we do know, which is at pi. And I'm going to draw the line tangent to that. Pretend that it's tangent. And I'm going to use that equation to help me estimate the sine of 3. Okay, so the function, actually, I'm going to stop, pause, go do it. Welcome back. How did it go? Hopefully good. So we're going to use the convenient point of pi comma 0 because we know that the sine of pi is 0. Okay, I'm going to use that convenient point, and I'm going to need to know the derivative. The derivative of sine is cosine. I'm going to then use my convenient point to determine the slope of that tangent line. So the cosine of pi is -1. That's my slope. So using point slope form, y minus 0 equals -1 times x minus pi. All right, if I plug 3 in for x, I'm going to get rid of that 0. We don't need it. I'm going to plug 3 in for x. And now you're thinking, oh, wait a minute, I don't know pi. You know pi is 3.14159. And so if you subtract 3 from that, it's just 0.14159, in this case negative, multiplied by -1. So we can say that the cosine of 3 is approximately 0.14159 and the rest of the digits of pi. Okay, let me try that in my handy dandy calculator. I'm going to find the sine of 3, and I'm in the wrong mode. Hold on one second. Actually, put it in your calculator because by the time I convert it, it's going to be too much. Oh, here we go. I found it. So 3 and then the sine of 3, I got 0.14112. Not bad. And then a bunch of zeros afterward. Okay, that's it. Only one video this time.